of the big catch-up. Apart from, well, Jazz's lesson actually came before, so it's not quite the beginning. But this is kind of the beginning of, the big catch-up, which is a series of live interactive lessons that we're doing over this week and next week to get everyone up to speed on all the stuff that, like, loads of people have missed over the past 5 months or so. With like two-thirds of all the students in the UK apparently haven't done any online lessons for like the past few months, and if you're one of them, then hopefully this will help you. And if you're not one of them and you've been lucky to have some lessons, then that is great. But hopefully this will get you up to speed on the key concepts anyway. So Ms. here, Rebecca Carmen's here, Roz here. Make sure you check out the sketch of what's coming up with the others as well. I'm just going to do a bit of physics and a bit of maths, and then there's some other people who are going to do chemistry, biology, English, philosophy, computer science, loads of stuff. Anyway, right, so thanks so much for coming, everyone. We will start with this. As I said, high school physics, speed acceleration, and mantis shrimp. But first, what's this? Spoiler alert, it's in the title. It is... this is a rainbow mantis shrimp. Does anyone know what's cool about a rainbow mantis shrimp and why I might be bringing one up right now? What is it? They're really beautiful. But they're kind of notoriously bad pets for some reasons. But anyway, I'm wondering if anyone knows. Like, does anyone know anything about a rainbow mantis shrimp that makes them kind of unusual or special? Miz has said that's actually acceleration. Have I spelled acceleration wrong? I'm always so worried I'm going to spell stuff wrong because I'm quite dyslexic. That is acceleration embodied. Yeah, I guess that is a reasonable idea. It kind of is, actually. That's why I wanted to bring it up. So no one knows what the deal with a rainbow mantis shrimp is. Okay, cool. It's not a mantis shrimp. Okay, so a mantis shrimp is this special kind of shrimp that has a punch that it can do with its larger claws that will go at, well, its punch can travel at, how fast do you think? This is the fastest punch in the animal kingdom that this little shrimp can deliver. How fast do you think its punch is? Punch speed. What do you guys reckon? What is the punch speed of the rainbow mantis shrimp? This thing 1 million miles per hour, not a million. Anyone else got any thoughts? 100 miles per hour. It's more like, 100 miles per hour is a pretty good guess. It's 50 miles per hour. It's the fastest punch that any animal has in the animal kingdom. And it's, what is that? Does anyone know what that is in kilometers per hour? Oh, Exodus Kings was so close with 60. So 50 miles per hour it is. Who knows what that is in kilometers per hour? Now, while people are guessing what they think that punch speed in kilometers per hour, did you know that there is a really cool way of converting between miles per hour and kilometers per hour that I only found out about really, really recently, and I'm just going to tell you it really quickly before we get into speed, acceleration, and mantis shrimp stuff. I don't know who remembers this, but there's this Roz has come in with 80 kilometers per hour, which is spot on, and so has Miz. So there's this thing called the Fibonacci sequence that goes like this. It starts with a 1, and then it's a 1, and then you add these two together, and it makes 2, and then you add those two together to make 3, and then you add those two together to make 5, and then you add those two together to make 8, and so on, and the sequence just continues like that. Now, I don't know if anyone else has ever seen this, but this sequence is an almost perfect conversion between miles per hour and kilometers per hour. 13 miles per hour is about 21 kilometers per hour. And you can always take two of these numbers, the next to one another, and it'll give you a good conversion. The only place where it doesn't really work is kind of towards the beginning of the sequence, but once you get far enough, it becomes pretty perfect. So you can use the Fibonacci sequence to convert between miles per hour and kilometers per hour. Anyway, that's just a quick Fibonacci trick that has nothing really to do with what we're going to do most of the time. How do you spell Fibonacci? My spelling is so bad. I think it's like that. Anyway, right, so yeah, the punch speed of a mantis shrimp is about 50 miles per hour or 80 kilometers per hour. The acceleration is like that of a small handgun, which is by far the fastest acceleration in the animal kingdom. There are actually trees that do faster acceleration with a kind of like spitting out of seeds, but we won't get into that. Anyway, the reason why they're such bad pets, even though they're kind of cute, is that if you keep them in a fish tank, then they will often literally punch their way through the glass. And like just destroy the entire tank. I'm not sure if it's cruel keeping fish in a fish tank. It feels like it is. I think any animal in captivity kind of makes me a little bit sad. But anyway, pretty cool that they can punch their way through a fish tank, because that's just kind of impressive. And Exodus is saying you can make it really thick glass, and Xenon, who's saying they look kind of scary and is maybe a bit late. These are mantis shrimp, so they have the fastest punch in the animal kingdom, as my quick recap. Anyway, right, so we today are doing speed and acceleration. Now, this is kind of focused on people who are like ages 13 to 17. It's going to be relevant to like all people of that kind of age range. If you're in the UK, it's going to be like kind of GCSE. It'll help for A-level stuff. This is also useful for like early IB stuff. But basically, regardless of where you are, these concepts are like the key concepts you need to know about speed and acceleration. Okay, right. First, I'm just going to close this window. Window closed. Okay, so let's go down here. So this is a speedometer, and it's just a classic speedometer that you get in a car. Sometimes you'd have like kilometers per hour if you're in like certain places of the world that are sensible and use sensible units for things, but if you're in the UK or America or a few other places, then you might have miles per hour. Anyway, so the reason why I wanted to show you a speedo is because the first thing I wanted to ask is, what is the equation for speed? So does anyone know what the equation is for speed? Equation for speed. And also, I'm noticing that quite a few people are joining late. I'm seeing 1 million slots is getting involved, and OMHNPH is here as well, and Exodusk is here. There's some new faces coming in. Anyway, okay, so people are saying speed equals distance divided by time, and that's great. So I think it's generally the first equation you learn in physics, that speed is distance divided by time. But I just wanted to make sure we did it as a recap. Now, if anyone did not know that or has had any trouble remembering it, the reason why I wanted to show you a speedo is because the thing is, like, in school, they often make you learn loads and loads of equations, and I remember being really stressed about it because, like, I'm crap at learning things by memory. But actually, loads of these equations you already know. You just don't know that you know them because they're embedded in other things that you know. So look at this. If you look at a speedo, it says kilometers per hour on it. Kilometers per hour. Kilometers divided by hours, which is a distance divided by a time. So the unit that you already know, kilometers per hour, is your distance divided by time. And it's same with miles per hour, because per means divide. Miles per hour. And so embedded in a lot of the things that you already know is the equation for speed. Speed is distance divided by time. Right, okay, so for those who... so some of you will find this a bit easier if you've done quite a bit of this before, but let's just do it as a quick practice. So let's go up to the mantis shrimp with its punch speed of 50 miles per hour. Let's say the mantis shrimp itself is waddling along the ocean floor with its trendy waddle, and it goes 30 meters, and it does that in 5 seconds. If it goes 30 meters in 5 seconds, then how quickly is it going? What is its speed? What do you guys think? Just in the Xenon saying they look scary. I think they are pretty scary. I mean, like, mantis shrimp will pretty much smash through almost anything in the ocean. So even if you've got like a really, really good protective shell, if they kind of get hold of you and just keep punching their way through, then your armor is eventually going to fall apart. It must be like being in those first medieval cities when cannons started to get used, and you always thought you were safe within your walls, and then suddenly there's not always cannons firing at the wall, destroying them. Anyway, yeah, mantis shrimp, they're like the cannons of the deep sea. Okay, so everyone's saying 6 meters per second, 6 meters per second, 30 meters divided by 5 seconds is 6 meters per second. Great, perfect. So just to run that through the equation, just in case anyone didn't follow, so speed is the distance divided by time. So the speed is the distance, which is 30 meters, divided by the time, which is 5 seconds, distance divided by time, equals 6, and then the unit of speed is going to be 6 meters per second. Brilliant. Okay, right. Let's do one more that's a bit harder. So let's say now our mantis shrimp is going. Let's say they're going at. Wait, we'll get a new thing. Let's say they're running at 5 kilometers per hour. They're going at 5 kilometers every hour, and they're going to do that for 20 seconds. How far do they go? Now, this one's a little bit harder because I've given you units that aren't in the standard form, and when you use a physics equation, you should always make sure you use the standard units. So write that down, 5 kilometers, if you've got a piece of paper. In fact, get a piece of paper if you haven't got one. Write down 5 kilometers per hour for 20 seconds. And then consider that the equation is speed equals distance divided by time, and that the standard units for all this stuff, speed is in seconds. So time is in seconds, and then speed is in meters per second. So because we got it in kilometers per hour, you need to convert that to meters per second first. Does anyone not know how to do that? 1 million sloths saying this is more maths than physics. Yeah, physics is so mathsy. But anyway, we're gonna get past the equations, but I just want to make sure everyone's on top of the equations before we crack on. Okay, so how do you convert 5 kilometers per hour into meters per second? So let's go on that journey. And let's move over here to make a bit of space for it. In fact, you know what? I'm going to get rid of all this stuff down here so that we got space for our converting our 5 kilometers per hour. So if you're going at 5 kilometers per hour, then you have to ask, how many meters could you go every hour? So if you go 5 kilometers every hour, then how many meters is that every hour? So yeah, exactly, 5,000 meters every hour. Great, now if you're going 5,000 meters every hour, then how many meters can you go every minute? Meters per minute. What do you have to do to get from meters per hour into meters per minute? So Rebecca Carmen is saying 30,000. So if 30,000 is a lot of meters to go every minute, if you can only go 5,000 every hour. So there are 60 minutes in an hour. And so if you're going to go 5,000 meters over the whole hour, then each minute you're going to go 5,000 divided by 60. Great. Which is going to be 83. Perfect. Yeah, Roz has got it. Yeah, so 83 meters every minute. Oh. Change that. So if you're going 83 meters every minute, then the next question is, how many meters can you go every second? And if you don't have a calculator, that's fine. Just tell me like how you would work it out. So how do you get from 83 meters per minute to how many meters you can go per second? So again, you divide it by 60 because there are 60 seconds in a minute. So if you go 83 meters over the course of a whole minute, then that means that in a single second, you're going to go about, I'm going to do it as a decimal now, you're going to go about 1.4 meters every second. So Rebecca Carmen's coming with 1.38. Great, I've rounded it a little bit, but you can go about 1.4 meters every second. So how far can the mantis shrimp go in 20 seconds going at this speed? What do you do there? So if you go 1.4 meters each second, yeah, 1 million sloths has got it as well, then how far can you go in 20 seconds? And Roz is saying, so Miz is saying 1.4 times 20, perfect, and Roz is saying 28 as well, exactly. So the answer is you can go 28 meters. The mantis shrimp will go 28 meters if it's going 5 kilometers per hour in 20 seconds. Cool, okay, really good. So the key idea there is that sometimes physics will like throw you the wrong units, and you just have to make sure you put the right units in, and then you can work it out. Okay. What if it is going backwards? Good point. In fact, we're about to cover stuff like that in a mo, so I'm just going to move over to this next bit. Right, this next bit is a chart of eggs on a graph. Okay, so this is another key bit of physics that we've got, a bit of maths that we've got to go through so that we can do the physics. So I'm just gonna, in fact, I'm just gonna like rub out loads of this bit because we don't need it anymore. Okay, that'll do. Get rid of those bits. Right, so if you've got these eggs on this graph, then what we need to know about is this idea called the gradient. So you can't do any of the speed and acceleration things until you know what a gradient is. So let's talk about what that is. Firstly, does anyone know what a gradient is? If you do, throw your ideas into the chat. Eggs indeed. Okay, Rebecca's saying, is it the steepness? Yes. Zaynon's saying the tilt of the line. Brilliant. Okay, so steepness is my favourite word out of those. And Roz is saying the same. Yeah, so the gradient is the steepness. So which one of these has the highest steepness? The orange one or the pink one? And for anyone who's colourblind, I'll number the eggs. So egg number 1, egg number 2. Which egg has the greatest steepness on the graph? Or the greatest gradient? And Miz saying the slope of the hill as well. Number 1, exactly. So number 1 is the steepest, most gradiential egg. Right. Okay. So how do you calculate this? Now I always remember it as being what's called the rise over the run. So how much does the line rise up divided by how much it runs along? So what I mean by that is if we look at this orange one here. Oh, let's get an orange color. Then it runs along. Let's say it runs along here. By 2, and then if it rises up by 18, then what is the gradient of this line going to be? So if it rises up by 18 and it runs along by 2, then what will the gradient be? Now, while you guys are working out what that might be, I'm just going to label some numbers on this one as well. So Zanon is saying 9, 18 over 2 is 9, and the y-intercept is 0. Perfect. Yes. Great. So the rise over the run is 18 divided by 2, so the gradient of this line is 9. And what's the gradient of this egg over here? And Roz is saying 2. Perfect. Yeah. So the gradient of the second egg is 2. So the gradient is the steepness, and you find it by just doing how much it rises up divided by how much it runs along. In other words, what is the change in y? That's like a classic physics symbol, this triangle. It means change. So what's the change in y? So how much does it rise up divided by the change in x? Now, this idea that gradient is... So gradient is the rise divided by the run. This is so vital and so central to understanding speed and acceleration, which is why I've made you guys go through all this maths. And we will talk about that in just a moment. But before we do, just because we've been doing loads of maths, I just wanted to show you this this frog on a running wheel. There's this really cool, I can't remember if I said this before in another lesson, but there's this really cool experiment that some people in the Netherlands did, because they wanted to find out, right, if we just put a running wheel in the wild, then are animals going to just come and randomly use it? Will there be animals that will just like keep coming back over and over again? It's just like running the wheel. And it turns out that they do. And so they found that there were like certain mice and things that would just like keep coming back and like running on the wheel for fun. They also found a slug like running on the wheel, although that was probably just a coincidence. And they also found this frog that I was showing before. Let me go back to it. This froge. Which is pretty cool. I don't know if the frog was doing it for fun or if the frog was just trapped, but certainly the mice did come back multiple times. Anyway, let's call it the fun frog for now, and maybe we will come back to the fun frog later. Okay, so key idea. I'm just going to grab this bit here. So let's just grab that and keep it. So the gradient is the rise divided by the run. Now the reason why this is so important is because you guys are going to get hit with stuff that looks like this. You're going to get hit with graphs that show you the distance versus the time. And these graphs, I remember looking at them the first time and thinking, these look so complicated. But once you get the key idea about the gradient or the steepness, everything about them gets so much easier. That's what I find anyway. So the gradient is equal to the rise divided by the run, right? So on this graph, the gradient is going to be the distance divided by the time, because the distance is how much it rises up and the time is how much it runs along. So what is distance divided by time? What does distance divided by time mean? And trying to remember the equation that we were doing before. If you do the distance divided by the time, then what do you get? I'm just going to do dist divided by time. Then what do you get? So Laura is saying speed. Ms saying speed, Rebecca Carmen's saying speed. Exactly, yes. The distance divided by the time gives you the speed. So if the gradient is the rise divided by the run, and therefore the gradient is the distance, because that is the rise, divided by the run, which is time, so the gradient is distance divided by time, then that means that the gradient is the speed. In other words, the steepness is the speed. Now, whenever you get any graph in physics, it's really, really useful to just try and figure out first what the steepness means, because when you know what the steepness means, it's a lot easier to navigate the whole thing. So let's take this mantis shrimp here that's on the graph. Now imagine you're the mantis shrimp and you're just kind of walking along. How steep is this first bit here? What is the steepness of this first bit? Alex came in with speed as well, which is great. What is the steepness of this first little bit of graph? Exactly, so Rebecca Carmen's saying 0, Zanon is saying 0, the steepness is 0. There is no steepness, and therefore the speed is 0, because the steepness is the speed. So the speed is the gradient. I'm running out of light. I'm just going to do speed is grady. That'll have to do. We'll stop at speed is grady. So the speed is the gradient. Let me just get rid of that so we can make a bit more space. And also, now we've done that, I'll get rid of this as well. So the speed is the gradient on this graph. So let's do numbers in a moment. But first, I just want to make sure that everyone can see what this means. So at first, there is no speed for this bit. Now let's look at this next bit of the graph. What happens on this next bit of the graph compared to the bit afterwards? So something is happening here, and then something else is happening here. What do you guys think it might be? And if you can't imagine it, then think about... let's just move the thing back. If you can't imagine it, then try to imagine that you're walking up this hill. How steep is this bit? How steep is this bit? Rebecca Carmen is saying zoom. Exactly. Yeah. So here is quite a steep bit, which means this is a high speed bit. And here it's less steep, which means this is a low speed bit. Now, what is the speed on this section at the top? And Laura is perfect on this as well, saying speeds up then slows down. So Alex, great answer as well. Steeper gradient to shallower. From slow, it goes from fast speed to slow speed because a steep gradient is a high speed. And Xenon is saying it slows down slightly. Perfect, great. And then on this section here, what happens? And while you guys are saying what you think, I'm just gonna shove some numbers on here so that we can figure some stuff out. So that could be 3, 6, 12. And Xenon saying 0 again. Yeah, so on this top bit, once again, the mantis shrimp is going at 0 speed. So let's start labeling up these different bits, because interpreting these graphs is a really important part of like the high school syllabus that everyone has to do. And also it becomes a really useful skill with that interpreting other graphs. And usually school spends loads of time on speed and acceleration graphs, but actually like it expands into being really useful for other things, especially if you get this idea that the gradient is equal to this thing divided by this thing. And as soon as you've figured out what that is, it will just become so much easier to follow. Anyway, so this first bit, as everyone already said, is not moving, and the word we use for that is stationary. So in this first bit of the graph, the mantis shrimp is stationary. Now, can anyone work out what the speed of the mantis shrimp is in the second bit of the graph? So here it's stationary, and when it gets to here, what is the speed that the shrimp is going? So have a go, and remember that speed equals distance over time. And remember that you need to use standard units. So distance has to be in meters, time has to be in seconds, which handily this graph is. So what's the speed that the shrimp is going in this second section? Okay, so Laura says 4, Alex says 2, Miz says 2, and Xenon says 2. Right, Laura, that's spot on. Alex, Miz, and Xenon, and anyone else who was thinking 2, this is a really, really classic trap that I put here just so that you can learn it, because this happens all the time. So when you're doing the gradient or the steepness, you need to look at just the bit that you need to focus on just this bit. So in just this section that we're looking at, just this one little bit of straight line, how far along is the run and how far is the rise? So we can see that the rise up is 12, but the question is how long is the run? How far across does this go? And OMNPH has got 2 as well. So Miz saying it's 12:03. Yes, exactly. So don't worry, absolutely classic trap, but that's exactly why I showed it to you. 6 minus 3, perfect. So the run along is, I've literally written a 6. Oh my god, I've tricked myself. Yes, the rise is 12 and the run along is 3. So just focus on this one section, otherwise you'll get tripped up. And so 12 divided by 3 means that the speed the shrimp is going at this bit is 4 meters per second. Now, really important point is that because the line is completely straight, that means that the steepness is constant. And because the steepness is constant, that means that the speed is constant. So often they'll want you to write next to your 4 meters per second or whatever it is, they'll want you to write that it's a constant speed. So constant speed is something that they'll keep trying to get you to say. It's a classic like exam phrase, like making sure you know that the speed is constant in that region. Okay, right, let's do the next bit. Let's see if everyone can work this bit out. So let me label on some more numbers. So this number can be 9. If it's going to work. This can be 9, and let's have this as being 15. So what do you guys think the speed will be in this next section that the shrimp ventures into? So we know that it's getting less steep, and so the thing we're going to expect here is that the shrimp is probably going to slow down. So we're looking for probably a slower speed than before. Okay, so Rebecca Carmen's saying 1, or Million Sloths is saying 1. This sounds good. So the run along this time is 3 from 6 to 9, and the rise up is 3 from 12 to 15. So distance divided by time, 3 divided by 3 is 1. So here we have a constant speed of 1 meter per second. And again, try to remember labeling constant speed to show that you can see that it's a straight line, and so the steepness is constant. Great, okay. Now, what about this section here, which I'll label now? What's going on here when the shrimp arrives in this bit? What do you guys reckon? I'll give you some time to think about it. And meanwhile, I'll just tell you about something that I've been thinking about, which is that whale mussels are black because they've got this amazing protein in them that's really good at hanging on to oxygen, which is so cool. Also, polar bear skin is black as well, which means they must look so different without that fur, and the fur must be so thick in order for them to appear as if they're white on the outside. Also, survival tip is that you if you ever end up in the desperate situation where you end up having to hunt and kill a polar bear, then you should not eat the liver, because the liver has such a high concentration of certain vitamins that are actually toxic to humans. It's a classic thing that explorers have done before in the past, eaten the liver of a polar bear and then died from overdose. Anyway, okay, so yeah, it's 0, he's having a break. Yes, this bit is the shrimp's break, so here we are stationary again. Right, now, here's the last bit. I don't want you to do any numbers for this last bit, I just want you to explain what's going on. So in this last bit, the shrimp is on this hill, and the hill is getting, think about how the steepness is changing. What's happening to the steepness as the shrimp goes down this hill, and try to convert that into words that describe what's happening to its speed. So, what do you guys think is happening? No, don't fall. You would eat that. You would be tempted to eat the liver if you're like desperately hungry. I wonder if there's a way to get the vitamin to get. I can't remember what vitamin it is that you can overdose on. Might be K. There are only like a couple of vitamins that you can really overdose on, as far as we can understand. Like most vitamins, you kind of, if you take loads of them, then they just like come out in your urine. Okay, so Rebecca Carmen is saying deceleration. Laura's saying it's a slide. He's fine. And Xenon's saying runs back faster and faster. So it sounds like Xenon has got the best answer here. So let's think about the steepness. So it starts off with no steepness, and then gradually it's getting steeper and steeper and steeper and steeper and steeper and steeper. So the more steep it is, the faster the mantis shrimp is moving. So here it's not moving very fast, and here it's moving faster and faster. So this is accelerating, not decelerating. It's accelerating because it's getting steeper. And so you need to think of, I know it's going downwards, and so that maybe feels a little bit like deceleration, but actually it's getting steeper, and that's the thing that's important. You've got to focus on like, what is the gradient, what is the steepness? The steepness is speed. So if it's getting steeper, then it's getting faster. But because it's going downwards, it means it's going backwards. So the distance is decreasing. So it's basically going back to where it started, getting faster and faster and faster and faster and faster. And yeah, I mean, it could actually be death for this mantis shrimp if this is the mantis shrimp trying to climb up a wall. Then yeah, this could be pretty dangerous for it. Anyway, yes. So just remember that if it's getting steeper, and try to imagine yourself. I literally like imagine myself walking along it as if it's like a mountain, and I'm like, whoa, this is getting steep. That means it's getting fast, because the steepness is the speed in this one. Okay, cool, right, that was really great. I want to do, we've got like 10 minutes left, and I want to now talk about acceleration. So, who knows, let me just get rid of this speed is gradient thing. So here are two basset hounds accelerating towards someone on a beach. Basset hounds are they're kind of really cute, but at the same time I just feel really bad for a dog that has been bred to just have that much of a burden that it has to carry around with like such short legs. They are cute though. Anyway, right, so acceleration. Who knows what the equation is for acceleration? Now, if you want help, the units for acceleration are meters per second and then per second again. So it's meters per second, if that helps you to figure it out, although we normally write it as meters per second squared. So acceleration is meters per second squared, and it means how many meters per second do you increase by per second? So how much does your speed increase per second? So Laura is saying speed over time, which is brilliant. So yeah, the acceleration is, I'm going to use this triangle symbol that often comes up in physics again. This triangle means change. So acceleration is the change in speed divided by the time. So how much does the speed change per unit of time? So let's say you go from 0 meters per second all the way up to 32 meters per second, and you do that in 8 seconds. What is the acceleration that you are experiencing? What do you guys think? And for anyone who's feeling a little bit lost in acceleration now that we've just jumped to a new idea, just to recap it again, acceleration is like that feeling of speed increasing. Everyone knows what acceleration feels like, because when you're in a car, you can feel the speed increasing. But the acceleration is how much you increase in speed per unit of time. So if you increase 100 meters per second in a single second, that's loads of acceleration. Whereas if you increase like by 10 meters per second and it takes you several minutes, that would be like a slow train, like slowly speeding up to its speed. So yeah, if you go from 0 meters per second to 32 meters per second, then your change in speed is 32. And your time is 8 seconds. And so the answer is 4, which loads we've got. That's so good. Yes. So 4 meters per second and then squared. So it's 4 meters per second. Great. Okay, let's try one before we do the last chart. And the last chart that we're going to do is like the really important bit, but I just want to see how everyone is with units, since I gave you a hard units one before. And let's just see if it's okay. So if you go from 5 kilometers per hour up to 20 kilometers per hour, not per second, kilometers per hour, and that takes you, let's say, 30 seconds, then what is your acceleration? So I'm going to talk you through this while you might be doing it, but if you get your answer faster, then throw it in the chat, and that's great. I'm just going to move 30 seconds down there. So your first thing to find is what is the change in speed. So your change in speed is 5 kilometers per hour to 20 kilometers per hour, so that's going to be 15 kilometers per hour. Now, we now need to convert this into a proper unit, because kilometers per hour is not a standard unit. So first things first, what is that in meters per hour? How many meters is this every hour? What do you guys reckon? While you're figuring it out, let's pop an old hat on this dog, since he's off to an important event, and she can also have a hat, since she too will be attending the event, and they both need to look very smart. I'm not seeing any answers come in yet. I'll give you a few more moments. 15 kilometers per hour means that it's going to be, so 1 million slots is saying 1,500, and it's more than that because there's 1,000 kilometers in a meter, so it's going to be 15,000 meters in an hour. So if it's 15,000 meters in an hour, then to get it into meters that you can go every minute, then you're going to divide it by 60. So 15,000 divided by 60 is going to be 250 meters every minute. So how many meters is that per second? Arista Bassett. So yeah, 250 divided by another 60 gives you like about 4.2 meters per second. So if you're increasing by 4.2 meters per second and it's taking you 30 seconds, then what do you do to find the acceleration? Let's get everyone's last answers in. Yeah, Laura's spot on with 4.16 meters per second. I've rounded that a little bit to give 4.2 meters per second. So if you increase by 4.2 meters per second and it takes you 30 seconds, then what is your acceleration going to be? And because we're starting to run short on time, I want to go to the other chart. I'm going to write in the answer and let's see what other people get so you can compare. It's going to be 0.14 meters per second, which the answers are all starting to come in for that, which is fantastic. So yeah, 0.14 meters per second squared. Cool. I wanted to just do another units conversion because those things often get people, and I wanted to make sure you can do it. Right. Okay. So now let's look at this one here. I'm gonna let's get rid of this a little bit so we've got space. How we can get rid of the mantis shrimp's element for a moment because we now don't have a mantis shrimp. Instead, we have this goose. Okay, so goose. The goose is going. So we've got our now we've put velocity versus time. Now I've started to use velocity, but for now just think of it as speed. So velocity is just speed in a certain direction. So I'm just going to label speed here as well. So we've got speed against time. Now, first things first, what does the gradient mean? Remember, the gradient is the steepness. So, and the gradient is calculated by doing the change in y, so the rise, divided by the run. So what is the rise divided by the run? The rise is speed, the run is time. So we rise up by speed and we run along by time. So what is speed divided by time? Or the change in speed divided by the change in time. Great dog emoji. Just come in there. Exactly, acceleration. And so if you know the equation for acceleration, then you should be able to look at this graph and pretty quickly work out that the gradient is the acceleration. The gradient is the same as the acceleration. They are the same thing. The steepness is the acceleration. So first bit, imagine you're this goose and you're on this section here. How steep is it? The steepness is 0. What does that mean? What does it mean for the goose that this section here has a steepness of 0? Now, while you are starting to figure that out, I'm going to start labeling some numbers on here so that we can do some, so we can figure out some stuff. So Miz is saying not accelerating. There is no acceleration, and that is spot on. So because there is no steepness for the first bit that the goose is on, that means that the acceleration is 0. There is no acceleration. And so, in other words, the goose is going at a constant speed. So this region here just has a constant speed of what? What is the constant speed for this region here? What do you guys think? Let's label it in blue. And for those who are expecting this to finish now, we're going to wrap this up in about 3 or 4 minutes. I just want to finish doing this chart so that you've got it all. So there is a constant speed exactly of 11 meters every second, which you can see just by looking at the speed on this side of the graph. So here we have a constant speed of 11 meters per second. Great, right. What is happening on this section here? So when the goose climbs up here, there is some kind of steepness, right? And because there's steepness, that means that there is an acceleration. So here the goose is accelerating. Now, what is the acceleration there? What do you guys think? What is the acceleration in this bit here? So we're going along by 2, and we're going up by 4. So the change in speed divided by the change in time is 4 divided by 2, which Rebecca Carmen has said is 2 meters per second squared. Perfect. So here we have a constant acceleration, and it's a constant acceleration because it's the same steepness. We've got the same steepness all the way up. So steepness is acceleration, so the acceleration is constant. Constant acceleration of 2 meters per second squared. Perfect. Right. What is going on in this region here at the top? What do you guys think is going on there? I'm just going to move the goose to the region we're going to do next, just because there isn't space at the top for the goose. Pigula is saying it might slow down because it might find it too steep. So Roz saying constant speed. Exactly. So at the top, again, we have a constant speed because the gradient is 0. There's no steepness, and so there's no acceleration. So constant speed of what? And Laura is saying it's 15 meters per second. Perfect. So constant speed of 15 meters per second. Right. Next bit is the bit that the goose is on now. So what's going on with the bit that the goose is on now? What do you think is going on with the steepness? And again, imagine being this goose, you're on the slope, and what does it feel like? What is the steepness like? So it's a nice downward slope. So it's a negative steepness, because steepness has this idea of like being, you're going upwards, but this is a negative steepness. Which means that you've got, I'm waiting for an answer to come in before I say what it is. So Laura is saying it's slowing down at a constant rate. Perfect. And Fairy Cat is saying acceleration. So this bit is a constant acceleration, but the acceleration is negative because it's going downwards. So we are going from 15 meters per second all the way down to 0 meters per second at the bottom. So we call this bit constant acceleration, you can say, if you say the acceleration is negative. But what a lot of people choose to say instead is that it's constant deceleration. So this bit here has a constant deceleration. Now, what is that constant deceleration? Who can calculate it? And Xenon is saying it is still acceleration, which is exactly right. So you can still say it's acceleration, but you have to say it's negative. In fact, let's label them both. So it's a constant deceleration. It's also a constant acceleration. And the different ways that you can label it are like this. So has anyone worked out the number yet? So what is the actual value of acceleration that's going on here? Again, think through the run along. How long do we... Oh, I haven't given you a number, so you can't calculate it. Sorry, let's stick a 17 here. So if we run along by 5, and then the rise is downwards, so it's a negative rise. So we're rising by minus 15. So what is the acceleration going to be here? I'll give you a few moments to figure that out while I just fill in the last couple of numbers that I didn't have before. Well, actually, let's just pop an 18 there and then we're good. So Rebecca and Laura are both saying minus 3 meters per second squared. Exactly. So the rise over the run, the change in y over the change in x, the gradient is minus 15 divided by 5, which is going to be minus 3. So the acceleration is minus 3 meters per second squared. Oops, meters per second squared. Now, if you prefer, you can say that it's a constant deceleration of 3 meters per second squared. And it's actually up to you which you do. But if you say constant acceleration, you have to put negative because it's slowing down. But if you say constant deceleration, then you don't have to write negative because the idea of negative is built into this idea of deceleration. Great. Okay, last two sections before we finish. So this one, what is going on here? And that's section number 1. And finally, what is going on in this section here, which we'll call section number 2. So Fairy Cat is saying the goose walks backwards. And that's right. Well, the goose is kind of, yeah. Oh, no, sorry. No, that's not right. The goose does not walk backwards because all of this has got a positive speed. So if you are, yeah, at all the points in this diagram, it's going in a positive speed direction. So it's still going 11 meters per second, 15 meters per second. All the way along this point is still going forwards. It's just going forwards at a slower and slower speed. So region 1 is stationary, exactly, because here is a region where the speed is actually 0. So that region there is stationary. And then region 2, you have to imagine being the goose, and it's getting steeper and steeper and steeper and steeper, which means what is happening? So Fairy Cat is saying the goose stops and then accelerates. So I'm going to imagine that I'm like walking up here now. It starts off quite shallow, easy to walk up, and then it gets faster and faster and faster, and you accelerate and accelerate. So it's accelerating, and the acceleration is increasing. So remember, the steepness is the acceleration, and because this is getting steeper, that means the acceleration is increasing. So as you're going this way, the goose is not only accelerating, but it's accelerating faster and faster and faster. Anyway, you won't have to do calculations about this kind of stuff until you hit like degree level, or if you want to like study physics much later, but I just wanted to show you that last bit. Final point to add is that, and we won't have time to cover this all now, but if you find the area under the graph, then it will tell you how far the goose has travelled. So if you find this area here, this blue area, by just looking at the shapes and being like, well, this is 11 tall and this is a square, and then you can kind of like look at this bit here as a rectangle, and this bit here as a triangle, and then this is another rectangle. If you add up all these areas together, then the total area underneath the graph will give you the total distance that the goose has travelled. So the area travelled is the distance. Now, you might be interested to know that this is because distance is speed times time. And to find the area, you're going to do the speed times the time. That's how you find the area of a rectangle. You do its height times its width. And so you're doing speed times time for every bit of area you find, and so that's why when you add up the area, you get the total distance that the goose has travelled. So that's why you know the goose hasn't travelled backwards, it's constantly been travelling forwards this whole time. Right, okay, great. I'm going to leave it there because we've covered loads and loads of stuff and overrun a little bit, but I hope that's been useful. It would be really good to know actually what you guys think of how this went. So do let me know in the comments, or if you want underneath the stream on the website, you can fill in the feedback form. But anyway, I'm going to be back actually in like an hour and 5 minutes, I think. So I'm just going to show you what's coming up next. So next we've got, yeah, I'm doing forces, momentum, and moments. Let me make this a little bit bigger. And then we've got some chemistry from Josh tomorrow, and Jazz is doing some art tomorrow. And then on Wednesday, Hannah is back with some Cells Made Easy. I'm going to do waves and refraction. And then Phil's going to do some English, how to write any essay. That's going to be amazing. I'm always amazed at the English stuff because I was so bad at English at school, and Phil completely transforms it for me. And also on Thursday, we've got an inspiring guest who is the amazing Dr. Sarah Pearson, who is going to talk to us about dark matter, and she is brilliant. So I hope that you guys will come to that as well. So pop that in your diaries. That's going to be 5 p.m. on Thursday. Sorry for those who are in like New Zealand and Australia. We had to do it a bit later because she's actually in New York, and so it's a bit difficult to make the time zones work. But yeah, if you're in Europe or North America or even the Middle East probably, then hopefully you'll be able to watch this and yeah, that'll be great. Yeah, thanks again for coming. If you haven't already, sign up for the schedule on our website, follow our socials, which you can find here, and sign up for the sign up for the mailing list on the website, and do please spread the word, especially if you found this helpful. If you think this is going to help you getting back to school, tell your friends that these are running. We've got loads still to come. We've got like 30 or so lessons to help people catch up on the core subjects, and I'll see you guys in an hour. All right, farewell, bye.